Ruby loves Unix, applying beautiful Unix principles to build a Ruby prefork server. I'm Sahil Muthoo on Twitter. I work for Concurrency Studios. Right now I'm busy building snapci.com. It's a cloud continuous integration and continuous delivery platform for seamless integration with Heroku. You should check it out if that's the thing that you like. Alright. Unix has been around for a very long time, close to 4 decades. The Unix programming model has remained almost unchanged and has been the same for the same amount of time. What that tells us is that the programming model has transcended languages and frameworks to jour. You could apply the same principles that you learn here to a Haskell project as well as you can apply it to a C++ project. Because the underlying system is the same and the model is unchanged and adopted by all platforms, languages and frameworks. Also, it's important to note that smart people have been solving hard problems for a very long time with Unix. And it would be foolish for us to not take from and not understand those learnings and not build upon them and embrace that programming model. So here are a couple of popular tools. All of us probably have used a couple of them at least. And all of them have something in common. What they have in common is that they have the smart Unix. So this is the Unix license plate over there. So all of them have adopted the Unix programming model to some extent, some more than the others. But all of them apply those principles. All of them will move the thing. All of them will use copy on write. All of them will share file descriptors. All of that stuff is important, and I think it's necessary for us to learn that. And I think every generation of programmers as us relearn the Unix programming model, and I think I'm relearning it. So, and this is why I'm sharing this with you guys. So, okay, starting off, man pages. So, man pages, everybody know what a man page is. You type man, or else you get to see a huge document. You type man bash, and it's like a 400-page book. So, man is the documentation of the Unix system. Everybody knows about that. But what I guess not all of us know is that the man pages are divided into sections. So here I mentioned that tell your kill 2 from your kill 1. So all of us are used to sending a kill signals to a process. But if you see some documentation, you'll see that it's mentioned as kill 1. Why is that? Well, the reason for that is because there's also a kill 2. What is the kill 2? Well, kill 2 is a system call. So the Unix man pages, as I said, are divided into sections. The first section is general utilities. The section number 2, which is probably one of the most important sections, is system calls. Section number 3 is system library, C library functions. Section number 5 is for conventions and special files. So it's divided into sections, and it's important for us to understand that these sections will guide you to the thing that you're looking for. So if you want to study a system call, you should look at kill 2 and not kill 1. So you have to type man 2 kill and not man 1 kill. So I was talking about system calls, right? What are system calls? The system call is just an API that the kernel provides. You want a pipe, you call the pipe through system call, and the kernel gives you a pipe. That's it. It's just an abstraction layer. You can use it for fun and fun. Another thing, Ruby was built for Unix hacking. Now, why do I say this? The reason I say this is because if you look at the system call mapping and you compare it with the methods available and the methods and functions available inside Ruby, you see that all of them map almost one-to-one direct correspondence. 4 kill process.4. You want to select on a list of file descriptors? Well, yeah, I will select. You want to send a signal to a process? Yeah, do process.kill. All of this is applicable inside Unix, and all of it almost has a direct correspondence with Ruby. Moving on. Any discussion about Unix and Unix programming is incomplete without talking about processes. Processes is where it starts and where it ends. Any running program runs inside of a process, inside the Unix programming environment. They are the atoms of the system. And it's best that we talk about this. And my talk is going to be divided into 2 parts. I'm going to cover processes. It's going to be a primer. So some of this stuff might be very simple for a lot of you guys. But I just wanted to do a quick run through and a primer on top of that. And then we'll move on to more advanced topics as to how we will build the concept that we understood to create a preforking server out of that. Alright, let's get started. Simple example. To fire up IRB. Type process.pid. What do you get? You get a number back. What is that number? That number is the process ID of that process.pid, I type process.ppid, I get another number back. What number is that? Well, that is the PID of the parent process. So processes have parents, they have a lineage. So processes have children and they also have parents. Well, they may have children, but they always have parents, except for unit, which doesn't have, it's like the God process. It's PID 0. So we see the lineage of a process here. So I have running IRB command and I print out the process tree of it. So this PSP -s IRB will select all the processes which have the name, which match the name IRB and print out the complete lineage of that process. You see over here that IRB was spawned by bash, which was spawned by item, which was spawned by launch key. And it goes up all the way up until the unit. Processes also have friendly names. What does that mean? Well, we were running a process and the program name of that process is IRB, but I can change that if I want to. I can call now my IRB is ponies. But is that useful? Why would I want to change IRB to ponies, right? Well, it is useful in some way. So this is a preforking server which I started up. It's called Kanta. Kanta is the name of it. So yeah. More about this later. So this is a preforking server that I started up, and this starts screaming out logs, right? So what I see in the log, what I'm logging is I'm logging the program name. After that, I'm logging the PID, and then I'm logging the log line. So I can see very clearly over here that Kanta master is listening on localhost 8080, and it's about to spawn 3 workers. And after that, the 3 workers come up in line. So it's very easy for a system administrator to see, yes, the Kanta master is doing his work, the workers are doing their work, I take this log, I can see which worker is doing what. So the program name is useful, especially for humans. Moving on now, another simple thing. Processes have resources. So processes have, like wherever a process is running, it can open files. Open files or open file descriptors. Well, open is a bit of a misnomer because there are no closed file descriptors or whatever. It's generally called open file descriptor. So you have a list of file descriptors. You get 3 file descriptors by default unless you close them, which are standard in, standard and standard out, which you use to talk to TTYs and so on. And they are assigned descriptor number 0 to 2. Well, I guess this is pretty simple stuff. But what's interesting to note over here is that everything is a file. All resources are files and all files are resources. So even if I open up a socket, that socket is also a file. I create a pipe. That pipe is also a file. Everything that the process sees is a file. And if you go to /proc on a Linux system, you won't work on a Mac, so it doesn't have process. But if you go to /proc and inside the PID of any running process, you can see all the open files over there. You can also use the ls command to look at it. So here we see that we open up a socket, the socket gets assigned another file descriptor number, which is 3. Okay? Pretty cool. Processes can fork. Now this is interesting. Processes can create new baby processes. And those new baby processes are replicas of their parents. What I mean by they are replicas is they copy over their memory and they inherit all the resources. So if you see over here, the child process has copied over the entire running Ruby processes and is a new running Ruby process now. Since it's copied over the memory, all shared objects, all open resources, what it means is that fork or that new child can also now execute Ruby code and we are printing out Ohio. What's interesting to note over here is if you look at those 2 red sections is that the parent process ID of the newly forked process is the PID of the running IRB process. So here I am just reinforcing the fact that all processes have children, and this is how it works. The process is fork, and if you want to transform this, and if you want to execute the ls command after that, you would have done an exec. But since we want to stay in Ruby, we do a fork and we have another running Ruby process. This is a very important concept. I want you guys to keep this in mind because we will be using it a lot of future slides. Here's just another mind-bending example. If you don't know what fork is or how it works, I'm forking and there is a if else block and both code paths are executing. Now that's funny, right? That never happens. Like why are both code paths running? Why is forked and didn't fork both being printed out? I haven't seen that happen. But the reason for that is clear once you add some logging inside. Now you see that the parent process was 705 and 705 fork. The new child process was 5306. That guy did not fork. So both code paths did not execute. It's just that Fork returns a PID inside the parent process who's forking. So that is a 2 key value. But inside the child process, fork is nil. So that's false. So the whole code must get executed, and this is just an interesting thing to examine. Fork is copy on write only. I just need to put this out here because I had said earlier that fork copies memory. The thing is that the kernel will only copy or the memory when it needs to copy. The only time when it needs to copy memory is when memory is changed. So when you go and actually want to mutate it is when it's changed. This is an optimization. Sadly though, up until Ruby 2.0 we didn't have good copy and write support because the garbage collector used to go and mark and street everything. So everything was written to. And once everything is written to, then you have the entire, all the memories copied over. So memory settings were not really, we didn't have those memory settings in Ruby, but now with Ruby 2.0 our memory setting improvements are going up and up because we can leverage copy and write much better now. Alright, this is a simple example. I think we've covered enough material to probably try and understand this example. Simple thing. I'm opening up a file called homework and I'm assigning homework to a kid. I'm forking it off and saying, child, go and do your homework. And then in my master, I'm checking whether that guy has done his homework or not. Right? Simple example. But there's a problem here. Problem is, daddy never sees the homework. Why does that happen? The reason for that is that he did not wait for my child. I need to collect the status back. So the wait PID do system call or wait PID inside Ruby. I can wait on the status of any child process. And I pass in a PID over here and this call will block here. If the status is ready, if the child has already exited, it's also interesting to note over here that the kernel will maintain a queue. If the child has exited earlier, it doesn't matter. I do a wait PID, it knows that the kernel will tell me that this guy has already exited, I move on forward. If it has not, I will block here until the child is exit. This is also very important when you need to synchronize between children and when you're leveraging for concurrency, you need to wait for your children. So yeah, wait for your children. And wait PID is a family of system calls. There are a lot of different kinds of them. And we're going to see another one on the next slide. So hold on. This is another one. So processes have exit statuses. I'm sure all of us pretty much know this, but I just want to reiterate that in Unix when you exit with an exit status. The process has a final chance to leave its mark. It tells you whether it is passed or failed. And a zero exit status by convention and by tradition only means that the process was successful. It is important, in fact it is very, very important to ensure that you do not return a zero exit status if you are in a failure state. Because other tools will break. Everybody relies on this thing. So we see over here a different kind of wait PID. Wait PID 2. This returns the PID as well as the status. I can then assert on the status, and if the status is 1, that means that if the status is non-zero, it's not necessarily 1. If the status is non-zero, that means that the process failed, and I can take necessary action. So here's an example I get of Tata. I send kill to one of the child workers. The master detects that this worker has gone down, pulls out his status. In this case, I send the kill and it gracefully terminated, so the status is 0. But in case I would have sent the kill -9 and it had not handled it, it would have been non-zero exit status. Or if it had encountered an exception in its worker loop, it would have been non-zero exit status. Moving on, processes can receive signals. We all used to kill -9 processes when they don't work, right? That's not a good idea. But anyway, more about that later. So here I just sent a sick term. Sick term means okay, just terminate, right? And it's the 15 is important. The 15 is just the number of the signal. There are like a lot of signals, and this is the 15th one. That's about it. So, but the interesting part is that I've been talking about killing a lot. Kill isn't only for killing. Right? When we say kill -9, we always do not do kill -9 and we can get rid of this process. This Java server Tomcat is not working. I need to kill it. Right? But kill is badly named. It's just one of the stupid stuff that there is. Kill is just used to send a signal. Right? I can send a lot of signals. So if you look at this code, right, simple code, it prints out an incrementing number every second, right? I send a 6 stop to it. 6 stop, the signal will tell the process to stop. It stops, but it doesn't exit. It just stops there. After that, I tell it to continue and it works on. Beautiful. You send a signal, you can manage processes. You send arbitrary signals to processes, they all respect certain, they will either document what they do different or they will, respect the normal signals here. So say IRB respects this problem and it works fine. There are a lot of other signals. I just want to talk about a couple of them here. USR1 and USR2 are just user-defined signals. You can make them do whatever you want. There's also an interesting signal, TTIN and TTOU. So how Unicorn handles it is if you send TTIN to the Unicorn master, Unicorn will bump up the worker count by 1. If you send TTIU or OU, it will decrement the worker count and kill one person. If you send winch, the signal to the Unicorn master, it will winch up all of its children, do all the cleanup in the master will stay alive and then fork a new Unicorn out of that. It's really powerful. This stuff is really powerful. You send signals to processes. Processes can send signals to each other, and you can send signals to processes yourself from the command line as well, which is also a process administrator. So I would urge you to read man send signal. It's a bit lengthy, but so anyway, moving. You can trap and redefine signals. So here I refuse to that. I got sent a signal, term, I don't die. No, I'm not going to die. Right? And this is not a good example. Please do not do this ever. Okay? So, a better example. This is a much better example. I have a child and it's working. The parent receives a sick term. What does the parent do? The parent needs to ensure that his children are cleaned up. Because when the parent dies, the child does not die automatically. Nothing happens to the child. You fork off 10 times, you exit the parent, nothing happens. All of them continue to run. You have to ensure that you clean up after your children. So what I do is I trap down over here and send the same, I cascade the same signal down to my child exits, after that I exit. So this is an example of why you would want to trap and redefine signals. Another signal. Children exit with sick child. When a child exits, the kernel will raise you a sick child. Signal delivery is async. The kernel delivers the signal. It is not up to you when you will get the signal, or you don't need to manage delivery of signals. The kernel will deliver a signal. So in this example, for example, even though you are in a type loop, you will get a signal. The kernel will pick you up and say, hey, your child is dead, you need to do something about it. So okay, here's another example. Here I am trapping sick child, pretty common example. You fork off few children. You need to, make sure that all of them are done working, and after that you want to exit. So you wait for, 3 children. You fork off 3 children. You trap sick child, increment around them. When 3 children are exited, you exit yourself. Now there is a problem in this code as well. Anyone who wants to take that? What's the problem? Sorry?
Each of the child will be 14 as well.
No, there's only one floor. No, that one. Sorry? On the handle? On the exit. Yeah, so the thing is that the parent may never exit in this code. Why does that happen? So we'll have to take a step backward. As I mentioned, the kernel maintains a signal key. And signal delivery is unreliable. When I say that, I couldn't find a good way to word this. So when I say signal delivery is unreliable, what I mean by that is that the kernel does not put hard guarantees on how many signals you will receive. Say for example, you fork off 3 children and 3 of them exit in quick succession. You are not guaranteed to receive 3 sick childs. You are guaranteed to receive at least 1. You can receive 1, 2 or 3. But you are only guaranteed to receive at least 1. What do you do in that case? So this is the solution for that. I've defined a handler over here. In my handler, I have to do some more housekeeping over here. What is that housekeeping? Let's focus on that. What I do is, whenever I receive a sick child, I call a special type of wait PID. The special type of wait PID takes two parameters. First parameter is -1. What that means is I don't care which child died, tell me when a child died. And the second parameter is process W from hand. What that means is, if no child is exited, please do not block me. I have other work to do. If a child has not exited, I don't want to wait here. I want to move on further. So what this ensures is that when I receive one sick child, I actually loop over all of my dead children and I make sure that I collect and read all of the statuses. And now this code goes on. Alright, last part of our process. Processes can communicate. Simple example, we all use pipes to, on the command. Well, you can use pipes inside the code as well. Pipes is like very easy to simple IDC. When you do an IO pipe call, you get a reader and a writer. We know that Unix pipes, they're one way. So you write here and you read here. You can't do both at both ends. So you have a reader and a writer. In a child, you block. You say, whenever I get a message, I'm going to do something. A writer says, okay. The master process says, yes, wake up. So receives a message, can do any work it wants. Simple, one way, IDC. And I need to, so the thing is that I want to touch upon an interesting thing over here is, as I said, when you fork, you inherit all file descriptors. What that means is, in this case is, or why am I doing a writer and a reader flows in basically where I don't need it, is because when you fork, you get both reader and writer in both processes. So you have two readers and two writers. And you don't need them at both places. So you close your extra users. You must ensure that you clean up extra file handles because file handles are an expensive resource. And there are limits on how many file handles you can have. One last thing. Select. This is extremely powerful. This is probably the most important part if you want to write a preforking service to understand how selecting on file descriptors works. This is very, very powerful. What you will do is, you can tell them, hey, here's an arbitrary list of file descriptors. Tell me when any one of them is ready for reading. Or here's an arbitrary list of file descriptors. Tell me when any one of them is ready for reading. So here in this example, right, I select on the reader. Whenever something is written to it, only then I am waking up. Otherwise, I am going to sleep. Well, in this case, I have a timer for 1 second. That's because I want to do some more housekeeping. You might get my housekeeping minute when I don't have any work. But anyway, you might want to do a lot of housekeeping, which we will see later. But the thing is that select will block and the kernel will ensure that you get notified when there is work to be done. This is the interface of select. I just want to highlight this because it's so important. You have a read array, you have an optional write array, you have an optional error array, and an optional time. In the read array, any file descriptor which is ready for reading, you will get notified in that file descriptor will be returned back. Same for writing, and same if any file descriptors have any interest. The optional timeout is if you want to do other work in between in a loop, and we'll see that later. Alright, second point, preforking service. What's that? Simple model. You have one master, you initialize whatever you want in your master. Say for example, if a preforking server is a Rails server, you generally want to load up Rails inside of your master first. After that, say your server is a TCP server, you want to create a socket first. You create a listening socket, you create your load up your Rails environment. After that, you immediately start forking. You fork 3 workers, they fork immediately. All of them have the Rails environment loaded up in them. All of them are sharing a file descriptor which is the socket. Now this is very important. What happens is you fork and you create workers, and after that you select on the shared socket. What that means is now you have just one socket. There is one socket. There aren't like 10 sockets to manage. So you have a concurrent server which can serve concurrent requests, but there is only one socket to manage. And all of them will share and listen on that socket. And they will select on it, and if something is ready for reading, they're going to try and accept a connection point. And we'll see more about it. Here are a couple of examples of popular preforking servers. RubyConf is the most popular example, I think everybody knows about. Passenger also it does forking into some effect now, though they're moving to a threaded limited model as well. I'm sure I'll have questions about why and why not. And this guy. This guy is just an there are a lot of concurrency in new age, right? Concurrency, there are a lot of concurrency models. This is probably one of the most simplest and oldest models. You want concurrency, all right. Create 3 processes. No concurrency, no process. Right? No threads, nothing. There are only processes, no shared state. So threads are hard. This is simple. There are trade-offs to this also. And I'm sure there will be questions about that. So what I'm putting out over here is that threads are difficult to manage. And this is a lot simpler. You don't need to care whether the code is thread safe or not. You fork and you're done. Faster to boot and more memory. So again, I'm going to take the example of Rails, right? Say you have a myriad job. You have like a background worker of some sort. And you want to make it concurrent. What you can do is you can create one background worker, load up the Rails environment, and fork it off. Say it takes 3 seconds to load up the Rails environment. One of your Rails tasks takes 3 seconds to load, right? If you need to load up the Rails environment 10 times to create 10 workers, that's going to take 30 seconds. But if you load up the Rails environment once and then you fork, it's going to take 3 seconds. It's not instantaneous as it is, but sometimes it isn't. But it's going to take 3 or 4 seconds, give or take. They just come up immediately. The kernel is very efficient at forking. It just comes up. Alright, simple example here. This is our master loop. So inside our master loop, I'm going to take small chunks of code here. So in our master loop, we spawn workers. What do? We create the worker, we set up the right state, we create a socket, we set up the PID and all the other stuff, we create daemonize and other housekeeping stuff, and then we fork it out. And then we collect that PID of that child. So if you see that workers hash will contain the list of PIDs, which is his children, which is manages. And then the master is going to babysit those. Master is going to ensure that they don't die. Master is going to ensure that they do it. But the master is not going to accept connections. The connections are accepted by the children or the workers. The master creates the socket and hands it out to the kids. They do the work. Master only babysits. So, one socket is shared amongst all workers. Now, there is an interesting aspect to sharing one socket amongst all workers. The aspect of this is that the kernel will load balance for you. So, if you have multiple workers and all of them are selecting on say the same, if you have multiple workers and all of them are selecting on the same socket. So, say suppose a request comes in, you open up the socket from the other side. You open up a TCP connection on the other side. What's going to happen is that the select can randomly, two processes can select the same. They say, yes, this socket is ready for reading, I'm going to wake up. They try to wait. But after that, they need to accept the client from out. So there is an accept. So if you look at this code over here, you select and then you do accept non-block. Now what this is the kernel ensures and guarantees that no 2 processes can accept at the same time. This is an atomic operation. When you are selecting from a socket, accepting from a socket, it's atomic. Select is everybody will get one. But accept is the kernel maintains that. So even under heavy load, it doesn't matter. You have a 36 core machine, you can have say 3 workers per core, do the math, you will scale up to that. It doesn't matter. The kernel will ensure that only one guy does work at one time and the work is distributed across all of them. You don't need, so there is no load balancing code inside of it. That all of that is pushed into the kernel. You don't need to write any load balancing code. So, and the other thing is that preforking servers are easier to sysadmin. What I mean by that is that they're managed by a signal from master, or I think I've already spoken about it. You send one signal, you send this TDOE to one guy, or say you send a stick term to Unicorn master. Unicorn master will ensure that all the workers are cleaned up and after that it cleans. So they're not like 10 processes to manage, only manage one process. So there isn't a jour process to manage, and it works with simple tools like it. So here's the example of how you will do it in your master loop, right? So you have a master loop running. Inside a master loop, you see over here that I'm shifting from a signal queue. So I'm maintaining a signal queue inside. Whenever I receive a signal, what I do is I don't handle it at that point in time. I defer the handling of that signal. What I'll do is I'll push that signal into a signal queue. And then I'll say master wake up. The way I wake up master is that I write to a pipe, and then in a non-blocking fashion I write to the pipe, and the master is selecting on that. So the master says, oh, this sounds work for me. Master wakes up and shifts from the signal queue. and pulls out whatever is the latest in the ready process. If you see this example, I have not handled basically handled stopping worker, so you will want to do that over here because there is another reading I want to talk about. Go TTI and VDOU. This is how we handle it. Simple stuff. You receive a signal, put it into a queue, pull it out from the queue, the loop keeps running. So there is a continuous loop inside the master and the worker. But that loop is not churning CPU cycles. I think that is very important to understand that even though you have a loop, since you are selecting on channels, the CPU cycles are not being churned because you go to sleep, the kernel wakes you up, or if the kernel doesn't wake you up, you wake up after some time, you do some housekeeping, you go back to sleep. So you are not churning CPU cycles anywhere. You start up RubyConf, it's not like it's 100% CPU usage. Because this is a loop, right? So if you run a tight loop, you're going to have 100% CPU usage. But that doesn't happen. The reason for that is because you select at points. You select on file descriptors, if they're not ready, you sleep for a while, you wake up again. So this is an example of sending a TTI into Nata and another worker. I think there's a small typo here. Alright. Couple of more idioms to talk about. Running the Unix up to 11. How do you kill hung workers? So the problem is that when you have a preforking server, sometimes your workers can hang, right? You have a long running request. Somebody is uploading a big file. It's hung. Problem is that you only have 3 workers. If it's hung and all 3 of your workers hang, you're doomed. Your preforking server is down. So what do you do in that case? There are a couple of steps to this. First step is that you hand each worker an unlinked temporary file. When you are creating your worker, you create a temporary file and you unlink it. The reason why you want to unlink it is because nobody else should be able to see it. So you create a temporary file, you unlink it, you sync it so that there is no user space buffering in it. And then you hand that temp file to the worker. And of course, you also keep a temp file with yourself. You as the master, you also keep a temp file. So each worker has a temp file and you have a temp file. Next step. The worker must chmod that temp file periodically in its loop when it's running. So you see over here, before I accept the connection, I chmod that temp file, and before I sleep for a select, I chmod that temp file. Now I know if I do not receive if the ctime of that file is not greater, if the ctime of that file is greater than the timeout, what that means is that that file is not being chmoded in time. And if that hasn't happened, that means that the worker is hung somewhere inside after it accepted its connection. And it's busy pursuing work and I can't do anything. Alright? I kill it with 0 trajectories. Kill worker. And after that, I spawn new ones. This is my main loop. If I don't receive a signal, I keep doing this all the time, right? I kill any workers which have run away and I bring new ones back up. No mercy. This thing has a name called fchomod heartbeat. Yeah. Alright. Now a simple thing, right? How do you read dead workers? So workers are dead, workers can die. There's an exception in the worker loop, it dies. Right? But I'm maintaining a hash there with the workers list of PIDs and their objects. So if those two go out of sync, then I'm in soup. So what do I do in that case? Same idiom I apply over here. I do a wait PID with a W no hand in my event in my master loop all the time. I see if it's died, I read it. I just delete it from the array, close the temp file, and I log it out. So this guy is down, and of course, a new one will spawn up after that. So this is like wait PID with W no hand. Another thing. Now, right now we are giving all the importance to the master. But what about the children, right? What if the parent goes away? The parent goes away and there are children like them. The child needs to go down with his parent. It needs to stay with his parent. The parent is gone, the child will say, no, I can't stay without my parent. I am going. Simple stuff. How do you do that? So, as I said, we are doing a non-blocking select. So, we time out our select after a while, right? So, in timeout by 2 seconds, I do some housekeeping. I go back and I check and I say, oh, The master PID which I was initialized with is no longer my process's PID. My parent is no longer there. My parent is somebody else now. Yeah, that's exactly what happened. So my parent is somebody else now. And in that case, no, I am not going to continue running. I am going. And that's it. Exit out. So timeout and I select by 2 seconds. Make sure that the master PID is there. And if it's not, yes. So there are a couple of more tricks. I don't think I have enough time now to talk about them. But there are a couple of more tricks which I think are important. How do you daemonize a process? How do you run a daemon process? So basically, it involves forking once, and then becoming the session leader, the process group leader, and then unlinking all PTYs and everything, and then forking out again. So you ensure that you do not have any PTY, and you ensure that you are now attached to it and you are a daemon process. Deferred signal handling. I think we'll talk about this a bit more, but I think it delivers. This is also known as the self pipe trip. So you maintain a pipe between amongst your inside yourself, and you use that to synchronize and make sure that. So the thing is that signal handling code has to be re-entered. You can receive a signal while handling a signal. So if you use a pipe to synchronize and maintain a signal queue, things become a lot simpler and you avoid these types. I'm done. Thanks. Please, questions? No.
Hi.
Hi.
Great talk. Thanks. So my question is regarding web servers and forking web servers.
Yeah.
So a web server is listening to a certain certain port, and when you fork, then all the forks or the children first also start listening to the same port.
Yes.
So how do you use this preforking funda in this problem?
I'm not sure I understand clearly.
So there is a web server listening to a certain port. There can't be many, more than one web server listening to the same port.
Yes.
So, but when you fork the web server, it inherits all the properties of the parent. So,
yes,
all the children listen to the same port.
Yes.
Which is not supposed to be happening.
Yes. The thing is that there is only one of them. There is only one socket. That socket. There is only one instance of that socket on that port. There is only one socket. You are right that you cannot have two open sockets on the same port. But there is only one open socket. All the children. So when you fork and you have a replica of it, of your child process, the resources that we inherit are the exact same thing. So there is just one instance of the socket. And all of them are listening on the same, and all of them try to sit, they are all race. So all the workers, right, they have a race. They see something is ready to select, they try to accept, they either win or they E again. If you look up man to select, you will see E again exception is raised. Try again. Because somebody else has won. Well, there are other conditions in which E again can be raised, but in our case, we know that E again from some other worker has won. Because we were woken up from select. That means that something at some point in time is ready for reading. But then when I tried to go and read it, actually, somebody else read it. So there is only one open socket. There aren't, if you fork three workers, there aren't three sockets. There's just one. You share, everybody share that. That's the basic principle of underlying principle of what we focus about. That the kernel load balancers are connected. The kernel will tell you when things are ready for it.
Right. So great talk. I'm pardon my ignorance, but you said like socket is like a file, gets a file descriptor as well, and you gave a concrete example of a socket. How does this work when you're actually reading a file, or let's say things like iNotify, where you're sort of like being, how does this translate to that?
So it translates in the same way. So if you see the example here, so say for example here, right? So I'm not using iNotify. Unicorn doesn't use iNotify. The reason why Unicorn doesn't use iNotify is because there aren't enough file descriptors to guarantee justify the need to use iNotify. iNotify you use when you have a lot of file descriptors you want to know. Select is a really old school thing. I just have one socket. So what I do is
have of like 300 MB into 5 MBs of memory it will take, because I mean each forking that you do is instantaneous, almost instantaneous, but it still takes up the same amount of memory as the master process. So will it be wrong to say that 5 workers that have been running with 300 MB each as a master process? So there are like 6 processes, six processes that are running with 300 MB each, which is like 1.8 gigs.
Yes,
right?
That is correct. So,
and I mean, I can see a problem of memory blow up still into this case. How does it deal in this case?
Yes. So first of all, that is correct. When you are forking, you will have memory blow, right? Because it's a direct emitter. So the thing is that first of all, the memory that you see, right, there's a lot of magic which happens in the background. So memory is cached, there's virtual memory, there's real memory, there's different kinds of memory. So even though you see that a lot of memory is being consumed, probably not all of that is being used. And if needed, that memory will get reallocated in other ways. But having said that, a forking server will consume a lot of memory. Let's say, for example, a threaded or event system. There is no getting around that. But the thing is,
there's also copy on write.
Yes, there is copy on write. I talked about that. But when you initialize it, invariably, so when Ruby starts with GC hits, it goes and mutates everything, and then So there is copy on write if your language supports it. But if you're talking in the context of Ruby, so Unicorn, right? When you're running Unicorn, say you have one code, you don't want to run more than 3 workers. You don't need one. And to run 3 workers, you just need, say, a gig of RAM. And that's the trade-off if you're running a preforking server. Yeah, you have a gig of RAM, you have 1 core, you run 3 workers, and you can't scale up more workers anyway. Because if you keep adding workers, the system is going to be it's going to go into salvage. It's going to swap all the time.
Yeah, so that's the reason when Passenger started, they implemented RE which had different GC, which doesn't do mark and swipe. So they can use copy and write and then use prefork.
So, and it gives around 30% of memory efficiency.
Yes. Obviously it's not 100%.
Hi. So I want to know how do you find out how many forks can you make on the master? What number do I?
What number? I just spoke about that. So typically, right? So these things are very, it's not that easy to talk. So it depends on your load, right? On your workload. If you have CPU bound workload, and since Ruby, if your Ruby code is not concurrent, then you can only have one worker. Because the other worker will never get time to work, right? But the good part is you're not CPU bound. You're waiting on an API. You're waiting to talk to the data. You're waiting for the write to come back to the data. Some things of that kind. So you need to limit the number of workers every time. As I said, a good number is per core you can have 3 workers or 2 workers. And you need to tweak it in balance. Because so if your IO on, when one guy is in IO, the other guy is in some CPU where they do the tasks.
Great talk, and since my talk tomorrow is about concurrency in Ruby, and you have covered part of what I talk about, but I talk about like when to use threads to solve these problems. So some shameless self-promotion.